Thank you very much, Joel. Thank you for inviting me, and also I want to thank Professor Menier for the invitation. So I think this is a very good idea of bringing together different scientists to talk about new things, new systems in which computers are involved as a main tool. So I will talk about two-dimensional materials. Of course, everybody, or I don't know if everybody, if not, then I will review, because the simplest two-dimensional material that we are going to call two-dimensional material is graphene. Have you heard about graphene? All of you? Well, that's good. Have you calculated the band structure of graphene? No? Okay, well, this is good. I see some of the students who took solid-state physics with me, so they know more or less what I am going to talk about, but I will extend my lecture because though some of the results I'm going to show you come from DFT, density functional theory, which is the first approximation as in ab initio or first principles methods. For some systems, it is just the first approximation. We need to do something else. And I will mention this at the end of my talk. I will emphasize my talk related to DFT, and I will mention some points in which DFT is not so good. So the outline of my talk is, first, we have to define two-dimensional materials. Once we define two-dimensional materials, we have to see what is the structure of these two-dimensional materials. You need to know where the atoms are in order to start calculating using your computer, right? Of course, once you are using your computer, you can calculate some properties, right? And these properties, I have put here physico-chemical properties. You can calculate the band structure, you can calculate the phonon dispersion, but you need to compare with the experiment. If your calculation does not agree with the experiment, then something is wrong. And this happens very often in calculations in general. So it is very important to know a little bit about what is going on with the experimental results. I'm going to talk about geometrical properties because two-dimensional materials offer a very interesting possibilities. And this is due to the fact that we can consider them sheets, two-dimensional sheets or quasi-two-dimensional sheets embedded in a three-dimensional space. And three-dimensional space restricts our possibilities. In fact, three-dimensional space plays a crucial role in the possibilities we can have. So I will mention these because from these geometrical properties you will see different possibilities. Some of them have not been studied yet. Some of the structures are waiting to be found. So that's why I consider this part important. And of course, I will talk about spectroscopies. This has to do with the characterization of two-dimensional materials. How can we characterize the material in which also, in a way that we have a reliable fingerprint of what is going on. And here in spectroscopies, I will talk about theory and experiment. Mainly, I will focus on Raman spectroscopy. I will not talk about infrared spectroscopy. Raman can be calculated with DFT methods, and infrared spectroscopy also. In fact, it is not necessary to calculate Raman. What is important is to calculate what we call the phonon dispersions. And I will mention that here. And what I will show you is how theory and experiment agree. And sometimes you don't have this agreement because the systems are more complex than your approximation. Bless you. Then I will talk about optical properties. It turns out that some of these two-dimensional materials, like Joel was saying, transition metal dichalcohenides, which I will show you what are those, exhibit very interesting are semiconductors. Graphene is a semi-metal or a zero-gap semiconductor. So if you don't have a gap, you cannot do very much with your optical properties. But if you have a gap and you have a particular features in your structure, you can have linear optical properties, and what is more interesting, nonlinear optical properties. So nonlinearities is a really very important active field in two-dimensional materials, and we know very little. I mean, we know that you have these nonlinear optical properties, but if you want to simulate them, things get more difficult. And the conclusion, then I will conclude more or less what we have seen and the importance of 2D materials, right? So let's start. I like very much this quote by Richard Feynman. I'm sure you know about Richard Feynman. What could we do with layer structures with just the right layers? What would the properties of materials be if we could really arrange the atoms in the way we want them? I can hardly doubt that when we have some control of the arrangement of things on a small scale, we can get an enormously greater range of possible properties that substances can have. Richard Feynman is considered the father of nanotechnology for this very important lecture that he gave in 1959, which is called There is Plenty of Room at the Bottom, that you can download in internet. So layer materials, at this time, I mean, nothing happened. Or in fact, perhaps something happened already. And I will explain why, because in 1946, the first indication of the interesting properties of two-dimensional materials was published. So as an advice, you students, most of you are students, undergrad and graduate students, is important to keep the literature up to date and know a little bit about the history of a particular system, because it happens all the time that you think, oh, I have discovered this, but turns out that this was discovered 50 years ago, or someone look at this, and you have to give the right credit. So I will show some of these about this history. So let's start concept of a 2D material. Do 2D materials exist? Or you may say yes, yes. And if we think strictly on 2 dimensions, because this D is for 2 dimensions, then strictly speaking, do not exist. Because then 2 dimensions is not even this sheet. Why? Because our atoms have a volume and are embedded in a three-dimensional space, right? So, strictly speaking, do not exist. However, if the atoms have, of course, if you have that the size of your system, your thickness of your sheets of these layer systems is very small compared with your flake or your surface, then you can say, well, you can define that this is a two-dimensional material, right? And what I have done here is divide the thickness of the surface to 1/2 in order to have an 8-dimensional number of a 10 microns flake, square flake of graphene, and this is the number that you get. So it is a very small number. So you can consider graphene, three-dimensional atom, forming a three-dimensional structure embedded in three dimensions, is what we are dealing in, strictly speaking, is a three-dimensional structure. But due to the fact that these are very thin compared with the size of your layer, your length, or your system, the length of your system, then it can be considered a two-dimensional material. Another feature of two-dimensional materials is that you need to differentiate the layers. So what happens if you put another layer of graphene on top of graphene? What happens is that it is not going to happen, it's not going to be a chemical bond. This interaction between layers is very weak. And this interaction, this weak interaction, for historical reasons, is being called van der Waals interaction, which is very complex and difficult to really implement from first principles. So you have that the sheets are very big compared with the thickness, then, and the interaction is van der Waals type, then you can have a 2D material. This interaction between these layers gives us a method, because it's very weak, the interaction, gives us a method to synthesize or to obtain monolayers. And this method is called mechanical exfoliation, but it is not other thing than that a Scotch tape method. You use a Scotch tape several times and then you can get something very thin up to monolayer. In fact, Andrei Geim and Konstantin Novoselov used the Scotch tape method that was known since long time ago, since transmission electron microscopes appeared, was known this Scotch tape method to get very thin samples, because in an transmission electron microscope, your electrons need to go through the sample. So if it's very thick, then you cannot see anything. And see, if you have add another layer or 3 layers, your system continues being a two-dimensional system. You have bilayer or 3 layers. The thickness is very small compared to the edge or perimeter. Okay, well, this is graphite, and here we have graphene. This is the graphite that you have in your pencil leads. And when you write, you deposit a few layers of graphene on your paper. And you can separate the interaction. There is no chemical bond, so you can separate them with the Scotch tape method. I'm putting here Euclidean geometry because in geometric properties I will come back. But if we look at graphene sheet, as a flat sheet, then all the geometry, the properties of the geometry that we have are Euclidean, belong to the Euclidean geometry. Like if we measure the interior angles of a triangle that goes from this point to this point and to this point, then the interior angles of the triangle will be, the addition will be 180 degrees, right? Okay, however, graphene is not the only one, which is very good. It's very good because all these systems have different electronic, mechanical, and optical properties, linear and nonlinear. So we have a hexagonal boron nitride, which is a crystal you can exfoliate, is an insulator, 6 EVs, electron volt band gap. You have a molybdenum disulfide. All these molybdenum disulfide, niobium diselenide, niobium disulfide, tungsten disulfide, all these are called transition metal dichalcogenides. Why? Because we have a transition metal. You look at in the periodic table and look for the transition metals, you will find that molybdenum, niobium, tungsten are transition metals. And chalcogen atoms, dichalcogenides, because have 2 chalcogen atoms per formula, and sulfur, selenium, tellurium are chalcogen atoms. So these structures, all these molybdenum sulfide, well, not all these, molybdenum disulfide and tungsten disulfide, in this structure, in this phase, because there are different phases and I will talk about, are semiconductors. And the semiconducting gap with the optical band gap is around 1.8 in molybdenum disulfide and 1.9, 1 or 2 in tungsten disulfide. It turns out these are semiconductors, but niobium diselenide and niobium disulfide are metals. They exhibit the same structure. This structure is called trigonal prismatic. I will define this structure, and I will show you how the phases that give related to this structure, which are called 2H phases or trigonal prismatic. All these are trigonal prismatic. Same structure, but of course different atoms, they have different electronic properties. It's not the same molybdenum than niobium, is not the same selenium than as sulfur, for example. These are not the same. And there are others that may be considered. I added here magnesium diboride because it should be possible to have a monolayer magnesium diboride. It's a superconductor that was very important a few years ago, like 10 years ago. Also, I have added here zinc oxide. Zinc oxide is a semiconductor, and it turns out that the structure in bulk is not layered. However, if you manage to cut a slice and isolate the slice in a particular orientation of your crystal, in a particular way, this is challenging. This has not been done. But with your computer, you can do it. And then you cut a slice of these along an axis that allows you to see these honeycomb lattice. And then you relax the structure. You will find that the structure is stable. You can find a minimum of energy. And when you add another layer, then you keep the layer does not stick through a chemical bond. You still have this van der Waals interaction. And you need to add several layers to start obtaining the Wurtzite structure, the three-dimensional structure. So this is a very interesting system. Okay, well, structure of graphite. Believe it or not, the structure of graphene was known more than 100 years ago. And this was known since people started to perform X-ray powder diffraction. So 1917, Albert Wallace Hall, Peter Debye, and Paul Scherer, they knew that graphite was made of layers, and the layers were separated by 3.35 angstrom. But the problem at that time was the stacking, how the layers are stacked to form a crystal. That was the problem, because what they had was a three-dimensional structure. And since they didn't have a good crystal sample, because the powder, it turns out that in the powder sample, if you take the powder sample from a mine, for example, of graphite, you have two different kinds of graphite. You may have FCC, face-center cubic graphite, or you may have also a AB stacking graphite, which now is known as Bernal graphite, because Bernal had a very nice sample. He was working in Cambridge at the age of 23 years old. Here is older. He is your John Desmond Bernal, and he, by X-ray diffraction, found that the stacking was AB stacking. So this is what you have, and you are able to calculate, and you can calculate it, the van der Waals interaction, considering the van der Waals interaction, because if you don't consider the van der Waals interaction, you will not see the difference between different stackings. Or you may get that two stackings have the same energy, are degenerate. So considering the van der Waals interaction, it should be possible to prove that this stacking is the most stable. That's why we see it in nature. But the problem at that time was solved by Bernal. He has noticed that in the proceedings of the Royal Society of London, William Bragg was the person who communicated this paper. William Bragg was his supervisor. I would like to mention that Rosalind Franklin also did a very important contributions on graphitic carbons, because there are carbons that they cannot have the 3.35 distance, so they have a different distance, and this is due to the orientation of the layers. This is called turbostratic carbons, and then this interaction, the distance between layers and turbostratic carbon, becomes 3.4. It's a very small amount, but is important. It's important because you lose the crystallinity in the Z direction. Okay, now this is about the structure of graphite and graphene. Now, what we can say about the structure of transition metal dicalcogenates. If we are going to consider molybdenum sulfide, tungsten sulfide, molybdenum diselenide, tungsten diselenide, niobium disulfide, niobium diselenide, for example, we have two phases which are the most stable. Is the trigonal prismatic, and it's called trigonal prismatic because here we have a trigonal prism. So this is your transition metal, and these are your chalcogen atoms, and you put together all these trigonal prism, what you get this structure. And if you look at it from above, you see this honeycomb, which is similar to the honeycomb you will see in graphene. There is another phase which is less stable. It is called the octahedral phase or T phase, can be T prime phase, and this is called 2H phase. And here, what happens is that the transition metal is coordinated with the chalcogen atoms in an octahedral way. This is an octahedron. You see the vertices where the chalcogen atoms are form an octahedron. And this is, it turns out that if you calculate, I mean, now, I don't know, you have started calculating electronic properties with your different codes. Professor Meunier talked about DFT. You can use different of the codes that there are in the market, or not in the market. Some of them are free. Siesta, BASP is not free, but Quantum Espresso is free. You can calculate the band structure of these two phases, and you will find that this is a semiconductor, and you will find that this is a metal. So you have two-dimensional materials. One is a metal, and the other one is a semiconductor. And both of them possess the same formula, a different phase. Okay, so we have talked a little bit about the structure of, there are other systems. I mean, there are other systems like rhenium diselenide, which the symmetry is, the only symmetry that rhenium diselenide possesses is inversion symmetry. So, but let's talk about properties, physico-chemical properties. This is what I was referring to before Feynman gave his talk. Wallace published this paper in 1946. And he calculated the energy dispersion and the band structure of graphene. In fact, in his paper, he called the band theory of graphite. But when you look at the paper, he says, since the spacing of the lattice planes of graphite is large, 3.37, in fact it's 3.35, compared with the hexagonal spacing in the layers, 1.42 angstrom, is the distance between carbon atoms in the layer. A first approximation in the treatment of graphite may be obtained by neglecting the interaction between planes and supposing that conduction takes place only in layers. So with this approximation, he is calculating graphene. And he used time binding method. Some of you already know the time binding method. You can use first principles, and I will show you how the band structure looks like. And the important message here is that the energy is related to the K vector linearly. Is not a parabola. So we have what we call a linear dispersion, linear energy dispersion. This was known since 1946, 1947. Okay, so of course he published this, and now it has a lot of citations. And I don't know, I don't know if he's dead already, but probably. Well, you know that Andrei Geim and Konstantin Novoselov got the Nobel Prize in Physics 2010 due to the experiments. They could prove that this linear dispersion exists. And these are very important because if you consider the Schrödinger equation, all the materials you study, the linear dispersion will be parabolic. So this is a different type of material which only works, this linear dispersion only works when you have a monolayer. And they performed experiments. They didn't discover graphene. I will show you. They performed experiments with Scotch tape flakes and prove that graphene exhibits this linear dispersion. And the electrons are in graphene behave as massless Dirac fermions. So this is what happens, the band structure of graphene when you calculate it with DFT or type banding. You have a linear dispersion of your energy, your momentum. As soon as you add another layer, you have a parabolic dispersion. You add more layers, and then you continue having the parabolic dispersion. So one layer is the important. I have calculated here with density functional theory using local density approximation the band structure of graphene, and here is where you see at this K point, called K point, in the Brillouin zone, this linear dispersion. So it's a good exercise that if you have already started with calculations, it could be good to calculate graphene. And you will, sometimes you may not get exactly this, you may get a gap, and try to choose more K points in your calculations and you will succeed. This is the density of states that show me that you have a semi-metal, this is a zero gap semiconductor. So this is with LDA. LDA works. LDA also works for phonons. LDA overbinds. When you calculate any system, doesn't matter which system, can be one-dimensional like in nanotube, or two-dimensional like in graphene, or three-dimensional in any other material, LDA overbinds. You will find that your lattice parameters tend to be smaller. And when you do general gradient approximation, it's the opposite. So it is not a good idea to do GGA, general gradient approximation, of graphite, because when you start relaxing, and you relax the cell and relax the positions then. So it's better to use LDA. Okay, so this is the first observation of graphene. This was done in 1962. This is in German, but Bohm, what they found is they were observing graphite in a transmission electron microscope, and they needed to exfoliate graphite. They did Scotch tape method, but this here you don't see clearly, but this shows that definitely the thinnest part is graphene. So they got graphene. So in all the review papers, the work of Bohm and colleagues should be mentioned. And also, people, we are not the first to think of monolayers and very thin structures. This is a paper, 1965, by Friend, in which he is working with electron diffraction, and he mentions that the crystals need to be almost transparent into electrons, I mean, in the electron microscope, and these can be prepared by stripping technique using adhesive tape. This is the exfoliating method, mechanical exfoliation, or a Scotch tape method. So this was known since a long time ago. And here is another, this is for Aluminium Sulphide. Friend worked a lot on transition metal dichalcogenides, and in this paper, a few years after, 1986, he mentioned monolayers. So one molecule thick sheets. But people didn't pay too much attention to these systems, which always happens. So it's a good idea sometimes to go to the library. Well, now you don't go to the library just to look what. There are lots of problems that have not been solved since years or decades, and perhaps need some attention. This is what makes transition metal dichalcogenides special. We saw that what makes graphene special is the linear dispersion at K in the brilliant zone. What makes special transition metal dichalcogenides, the semiconducting ones. So, I mean, molybdenum sulfide, molybdenum diselenide, tungsten sulfide, tungsten diselenide, is that when you have a monolayer, you have a band structure similar to this one, in which your band gap is direct. Is not indirect. Indirect means that in momentum space you have a different momentum. Here you have in the same K the transition. Here you have that here is in gamma, and your transition needs to be from gamma to an intermediate point between gamma and K. This is called Q or I. This is in bulk, right? But so this is important because once you have a direct band gap, you can have interesting electronic optical properties. Okay, so here what I have done is I have calculated with tungsten diselenide, I have calculated with LDA, DFT, monolayer, bilayer, 3 layers, 4 layers, 5 layers, and bulk. And the only one that exhibits a direct band gap is the monolayer. As soon as you put the other layer, just as in graphene, you put the other layer, then in this case, your direct band gap disappears. And of course, as soon as you put the other layer, you are changing the geometry of your system. You are changing the symmetry, even if the interaction is very small. So this is a good exercise, again, to calculate with DFT using LDA. You can use GGA, monolayer, bilayer, 3 layers, and then you will find these results. Here, I have to mention that since molybdenum and tungsten are very heavy, are very big atoms, you have what it is called a spin-orbit coupling. So that means that the spin of the electron couples with the movement, its trajectory. And when that happens, then what you have is a splitting in some points of the brilliant zone. Here, the splitting is at K in the brilliant zone, which is one of the vertices of the brilliant zone, and this has important implications for optical properties and also electronic properties, because in absorption experiments, you can find that you can see this transition, which is called A transition, and this is B transition. Or in other words, A exciton and B exciton. What happens? When you excite one electron goes from the valence band to the conduction band, right? So when the electron is here, leaves here a hole. So you have an electron-hole pair. It turns out that the electron-hole binding energy in these systems is very big. Perhaps the biggest you can have. so far. It's very big in these two-dimensional systems, which also you have to consider in your calculations. And when you consider this in your calculations, DFT is not enough, right? In fact, DFT is not enough for calculating, is not the best for calculating band gaps. Did you see this with Professor Menier? So what you need to do is to check the experiment, and you will see that DFT underestimates the band gap. And this is through, there are several reasons for this. There is a very important paper by John Perdue that explains everything about the underestimation of the band gap. So it's important to take into account. It turns out that, so when you excite an electron with, let's say, monochromatic light, a photon, and you form this exciton, there are two gaps. The electronic gap, which is the excitation from the valence band to the conduction band, and then the optical gap. The optical gap is smaller, is what happens is you need energy to form your exciton, and the energy is around 0.4 EVs. So your optical gap, once you have your exciton form, you are going to have a smaller gap, which is called optical gap. That means if there is a transition, I don't have it here, I should have one. If there is a transition, the optical transition that you will see will be from the optical band gap, not from the electronic band gap. And to consider excitons, you need to use another level of theory that considers the two particle effects, because you have an electron and hole. And this is called BSC, Bethe-Salpeter approach. Okay, I will mention this at the end, and I will show a graph in the context of nonlinear optical properties. Okay, so I show this because it turns out that I was working with colleagues in theory and experiment, and we found, I mean, we were not the first. Professor Reshev Tene from the Weizmann Institute in Israel found that you can get nanotubes out of molybdenum sulfide and tungsten sulfide. So we decided to calculate the band structures, and what we found is that for a particular structure, I'm not going to get into the details, armchair or zigzag structures, the particular structure is the way you roll up the sheet. You can form a tube. You can also do this with graphene and form carbon nanotubes, but you can have chirality if you do this, or you can roll it in this way. So there are different ways. So it turns out that in one of these ways you get an indirect band gap, and in the other way you get a direct band gap. So now one of the things I see is that people now are becoming interested again in these tubes, because depending on the diameter and the structure, you can have a direct band gap, which is very good. You can, in fact, tune this direct band gap depending on the diameter. Okay, I will go very quick. Another important thing that I think is important to mention is that if you are going to perform calculations on materials, different materials, does not need to be two-dimensional materials, it's important to keep a strong collaboration with the experimentalists. It's the best way, because the experimentalist will tell you I have this problem. I don't understand why this is happening. And then you can perform the calculation and try to understand what is going on. So I will mention this briefly. And also it is important to know what the methods, experimental methods, are involved. And here we have Scotch tape. This comes from Wikipedia. It's Andre Gein tape. So Scotch tape method, not high tech. And here we have what is called chemical vapor deposition method. Chemical vapor deposition method consists in putting tungsten oxide or molybdenum oxide in a furnace. And then you put the chalcogen atom, so you put a transition metal oxide here, you put your chalcogen powder here, sulfur or selenium. You heat this independently because the temperature here is around 900 Celsius. The temperature here should be around 200, 250, just to evaporate the sulfur, and then you have argon here that carries the sulfur to this place where it is being heated, and there is a reaction. And from this reaction, what you get is a small film. This is where you have your monolayer or a few layers. All depends on how you have done it. With the Scotch tape method, you cannot control the number of layers and also the size. Here it is better for the size, and also it is better for the number of layers. However, this one, it is chosen because it has less defects. And people are working like crazy trying to obtain something, CVD conditions with perfect, because defects degrade your electronic properties, right? And also, it is important to calculate defects. But I'm not going to talk about defects. Geometrical properties of layers. One thing which is important to think when we have layers embedded in a three-dimensional space is that these layers can be considered as two-dimensional surfaces embedded in a three-dimensional space. And then we can use differential geometry to generate new structures. Because you, as a physicist or material scientist, the first important thing you need to do before calculating is your structure, x, y, z coordinates, right? So understanding geometrical properties is important to get these x, y, z coordinates. Well, I will start with a little bit of differential geometry. Here we have that two-dimensional surface embedded in a three-dimensional space, because we need to work in 3 dimensions, exhibits, there are two principal curvatures, just two principal curvatures. And this can be proved in differential geometry. We call C1 and C2. And the product of these curvatures is called Gaussian curvature. And the mean value, the average, is called mean curvature. And here we have that the product is negative, is smaller than 0, and you form a saddle. Here the product is positive and you form like a piece of a sphere, right? And also what we have here, normal vector. In this case of a cylinder, the product of the two principal curvatures, one is in this direction, which is 0, and the other one has to do with the inverse of the radius of the tube. The product will be 0. Okay, in a cylinder will be 0. And this makes sense because a flat sheet has 0 curvature, right? It's not curved. And if I do this, if I write a distance between these 2 points in this sheet, and I roll it, the distance will be the same. though now it is curved. These are called isometric. And so it is, but the curvature has changed, but are related. It turns out that in 3 dimensions, there are just 3 geometries. So the space restricts the possibilities just to 3 geometries. There are no more than 3 geometries. You want to have more geometry, you have to go to higher dimensions. But of course, in some approaches, like studying the quasi-crystals structure, you have to go to higher dimensions and project to 3 dimensions in order to have an idea on what is going on with the structure of quasi-crystals and the concept of quasi-periodicity. But in this case, we don't go too far. We continue working in 3 dimensions, and the 3 geometries that we can have for surfaces are Euclidean geometry, you are very familiar, spherical geometry, and hyperbolic geometry. If you perform the experiment of drawing a triangle on the surface of an apple and measure the interior angles of the triangle, you will find that the interior angles of the triangle will be greater than 180 degrees. It will not be 180 degrees. If you do the same experiment on a horse saddle, you draw a triangle and measure the interior angles, then you will find that these are less than 180 degrees. So this belongs to hyperbolic geometry. Also, in Euclidean geometry, the Gaussian curvature is 0. In spherical geometry, the Gaussian curvature is greater than 0. And in the hyperbolic geometry, the Gaussian curvature of the surface is smaller than 0. These are constant Gaussian curvature. Here, the curvature is constant. The Gaussian curvature is constant, and also the Gaussian curvature is constant here, right? It turns out that, of course, you can embed surfaces in 3 dimensions. Here, your system is closed, is compact, then there is no problem. But it turns out that you cannot have a surface of constant Gaussian curvature embedded in 3-dimensional space, because what happens is that you start having self-intersections. And of course, this is physically impossible, although mathematically possible. And so what we do is we escape from the restriction that all points need to have constant Gaussian curvature. And we move some points, adapt these points, but we keep the angles. We keep the angles, right? Like a conformal mapping. You can move, but you keep the angles. And it turns out that you can, if you move a little bit your surface out of being constant Gaussian curvature, you can embed this surface in 3 dimensions. And here we have these triangles, and I will explain this later, how we can construct these structures out of graphite and graphene. But before that, I just want to show you that nature uses these 3 geometries in different systems at different levels of complexity. This is the skeleton of the echinoderm that has died. These channels are filled with organic matter, soft matter, and when it dies, then you get these regions where you have almost a periodic structure in which you have saddle points. In water lipid surfactant systems, you have Euclidean geometry, you have spherical geometry, but also you have hyperbolic geometry. It's a different scale, this is a higher scale. This is the eye of a bee. If you happen to have access to a scanning electron microscope, you can take an insect. It does not need to be a bee. don't kill it. Just try to find an insect which is already dead. And then you have to prepare the sample, cover the eyes of the insect with gold, which is done, people that work in scanning electron microscopes does it. And you will find that the center of the eye of the insect is made of hexagons. Almost perfect hexagons. And you know that with hexagons you can fill the plane, right? So up to infinity. However, the eyes of the insect are not infinite. They just have small eyes, right? So if you look at the edges or the ends of the eye of the insect, and you will see that not all are hexagons, but you find some pentagons. And these pentagons, what these pentagons do is that the pentagons curve the surface of the eye to end the eye. So they play an important role in adding curvature to the flat part of the eye. So at different levels, nature uses curvature. Uses positive curvature by introducing pentagons, uses negative curvature, zero curvature here, in these bilayers or here, and uses negative Gaussian curvature in these faces. So also at the atomic level, it should be possible to have positive Gaussian curvature and negative Gaussian curvature. And it turns out that this has been found. Have you heard about C60 or buckyball? I have here mine, which we use a 3D printer. So this is the buckyball. So in 1984, Harold Kroto, Bob Curl, and Richard Smalley and two students, they perform a experiment with an electric arc in which they use graphite rods. And what Harry had the idea, Harry wanted to see is if he could reproduce the conditions in red giant stars to see if chains of carbons can be formed. He was interested in chains of carbons. And it turns out, to their surprise, that using a mass spectrometer, because you perform the arc discharge, then soot comes all over your chamber. With a mass spectrometer, you can see what is the size of the molecules you have, and what they found is that there was a peak, a huge peak in 60 carbon atoms, and a smaller peak in 70 carbon atoms. So after some time, they decided that the structure should have this shape, the shape of a soccer ball. And this is the most symmetric structure you can have, with 60 carbon atoms with 60 vertices. The symmetry is icosahedral symmetry. If you truncate an icosahedron, you get this structure. And here you have this C60 can arrange in the vertices of a FCC of a cube and in the center of the faces to form fullerite, which this exists. Of course, this was 1984. In 1991, Sumo Ujima found in a sample that he was given by a colleague that also you can form tubes. Here are carbon nanotubes, concentric tubes, so it's like taking lots of these and then you roll up them, and then you have your concentric several layers, is what we see here, several layers. And the distance between these two layers is 3.4, because the stacking is not ABAB, is a different stacking, it's turbostratic stacking. So it turns out that what happens in fullerenes is that pentagons curve the structure in the same way as in the eye of a bee, and you have a family of fullerenes, C60, C70, C84, C82. People have not found this C240, but is the next icosahedral symmetry structure after C60. It's very difficult to separate the structures. So you also can calculate molecules with DFT. If you are interested, for example, in if you have a VASP, for example, or quantum espresso, those are designed for crystals. But you can calculate the properties of molecules if you put inside of the box the molecule, but you need to give enough vacuum so the molecule does not interact with the other molecules. And you may get a good approximation. What I advise is not to do that, but use another program which is called NWChem that works very nicely with molecules. But you can do it. Here is Sean O'Brien, Rick Smalley, Bob Curl, Harry Croto, and Jim Heath. These were the 2 students. In fact, there were 3 students who did all the job, and they 3 got the Nobel Prize, because the Nobel Prize just can be given to 3 people. So they have not changed. So what is interesting, and I mentioned, is that you also can have tungsten sulfide nanotubes. And these are images of tungsten sulfide nanotubes. The distance between these layers is 6.5 angstrom. These are bigger separation. But these are tubes that have been synthesized, so that means that also can acquire curvature. And there are fullerene-like structures out of tungsten sulfide, but are very big. And for these structures, a particular kind of defect or particular kind of arrangement needs to be introduced. Instead of a pentagon, you have a square-like system. So I will go very quickly because I want to finish on time. So here I have, it turns out that there was a mathematical problem. The mathematical problem was since the 19th century. I would say perhaps before, 18th century. Given a closed boundary, find the surface that minimizes area. So it turns out that this problem can be solved experimentally by closing a wire in the shape you want and submerge this wire into a soap solution. Then you will get a film. This film will minimize area, and in fact is a minimal surface. All the points in this film have zero mean curvature. And this is because you have atmospheric pressure at both sides of the film. However, when you mathematicians want to do this very formal, and it's not so easy. So this is called plateau problem. But there is an additional problem, which Hermann Amandus Schwarz solved. Hermann Amandus Schwarz was a student of Karl Weierstrass. Karl Weierstrass is one of the perhaps fathers of minimal surfaces, and he found a way to calculate minimal surfaces, right? Which is called now Weierstrass parametrization. But Weierstrass told his student, well, now your problem is to see if you can have periodic minimal surfaces. And the first thing I want you to do is three dimensions, periodic in 3 dimensions. In other words, crystals. Of course, if you look at this work, this was before electron diffraction, before space groups, before several things. And what he found is that you can have these minimal surfaces. And I'm just coming back to the Poincaré stereogram or Poincaré disk, and here I'm going to use this piece in which we have, all these pieces are the same, have edges or angles of 45, 90, and 30. All of them have these. And I mentioned that you have to change, you don't change the angles, you just change the Gaussian curvature a little bit here, and you can get a triply periodic minimal surface embedded in a three-dimensional space. Here, if you consider the angular deficit, you add these 90, 30, and 45 with 165 less 180, or 180 minus 165, you have 50 degrees of deficit. So this is a hyperbolic geometry. And with this piece, you can construct a periodic minimal surface. This is the piece, 45, 90, and 30, which you put inside what is called asymmetric unit, and you construct this structure, right? So why this is important? This is important for materials because you can decorate these structures with not only carbon atoms, but also other types of atoms that form two-dimensional materials, right? You can add negative curvature to these flat layers and have new possibilities, interesting properties and possibilities that people are studying. So this is what is called the gyroid structure. This is the gyroid. Here, what is the trick if you want to decorate these minimal surfaces with carbon atoms? The trick is, instead of introducing pentagons to have a closed structure, you introduce heptagons or octagons. And heptagons and octagons are very stable because the angles between first nearest neighbors, these angles, are very close to 120 degrees, which is the same angle that you have in graphite or graphene. So if you introduce these octagons, you can produce these periodic structures that people have called Schwarzschites in order to Hermann Amanda Schwarz. Some of the students, my students in solid state physics, we get coordinates for these systems. And this has been published. If you're interested, send me an email, and you can, it's a challenge because when you start increasing the size of the structure, this one has 192 atoms, 192 per cubic cell, then you will need more resources. And thinking of that, of course, with DFT, you can perform calculations up to a particular amount of atoms, right? I mean, perhaps hundreds, perhaps 1,000 atoms, but no more than that. So what we have done with the undergrad student here at RPI is consider these giant Schwarzschites, in which the number of atoms can range to 24 per cubic cell to 9,000 or 12,000 per cubic cell. And of course, you cannot calculate the electronic properties of these. So what you need to do is to use an empirical potential, Ribot, Terzo potential, force fields, and use code like LAMPS or GULP. This is very interesting because when you calculate these very big structures, of course this cannot be done with DFT, but I will show you what you would get with the smaller of these structures. This is, for example, something like you see. This is putting the atoms on the minimal surface, and when you relax the structure, you introduce your force field. The graphene likes to be flat, and then everything becomes flat. And here in this structure, you start having ripples. In fact, graphene likes to have ripples. And we calculated the mechanical properties. Here is the number of atoms. Look at this per cubic cell, 12,000. This is 6,000, so this cannot be done with DFT. If you try to do this with DFT, it will crash. These are lattice parameters, densities, and elastic constants. Elastic constants, these are cubic systems. These are the only elastic constants that are non-zero. You have a 6 by 6 matrix, and this is the bulk modulus. So you can calculate mechanical properties, but you cannot use DFT. And this is a very interesting result. Some undergrad students, one of them Javier Alarcón, what he decided was, I will put defects in particular places and calculate, relax the structure with lamps and calculate one of the properties that all systems have, which is called Poisson ratio. Have you heard about Poisson ratio? When you compress this structure here and here, all materials tend to expand in a perpendicular direction. Or if I pull these, this becomes a smaller diameter, right? But what happens, so this means positive Poisson ratio. What happens if you find a material when you compress it, instead of expanding, or when you pull it, instead of decreasing the diameter here, increases? So this is counterintuitive. These are called negative Poisson ratio systems or auxectic systems. And you can have, the problem is to synthesize this structure. People have not been able to synthesize this structure. People are working. So I will change gears, and I will go very quickly with a very interesting case, which is the gyroid we call G83, and we call G83 because we have the 1, 1, 1 direction, the center of this hexagon. Here we have 1, 2, 3, in fact it's this one. 1, 2, 3 hexagons and an octagon. Here we have 1, 2, 3, here 1, 3 hexagons, 1, 2, 3, and an octagon. So we call GA3, and this one we can calculate with first principles. My colleagues in Louvain-la-Neuve, they like to use Siesta. It's faster, and for this it can be used. It's not a plane wave code. They in fact were the ones who designed Avinit. Why not to use Avinit? Well, they decided to use Siesta. But here is the band structure, and here you can see these, which look like in this point of the Brillouin zone. Now remember the symmetry. Now this is cubic symmetry. This is a structure that belongs, the primitive cell is a body center cubic. So we change when the symmetry changes, the symmetry points in the Brillouin zone change. And now this is a three-dimensional structure. But these Dirac cones appear, but do not appear, this is a metal by the way, do not appear at the Fermi level. They appear displaced. But it turns out that since octagons are more reactive, and you can calculate that, you put in an octagon. In graphene, if you put something on top of graphene, it will not interact very much. It's quite inert. So, but here, where the octagons are, because this structure is negative Gaussian curvature, you can put lithium, add lithium. Lithium intercalation in carbon materials is very well known, and then with lithium, you can shift the Fermi level to be very close with to zero. So this is, and with Professor Meunier, we calculated different gyroids and found these Dirac cone, hyper Dirac cones, because we are now working in 3 dimensions. Okay, so there are several possibilities. It's important to understand the geometry to propose new structures that may have important properties. I go back to this structure because this is tungsten disulfide. Molybdenum disulfide tubes look the same, but I was interested in how to introduce positive curvature. How can we close these structures, keeping the stoichiometry? That means the relation between tungsten and sulfur atoms. And using the same principles as with graphene, I found that you can use this square-like defect or this octagonal-like defect, this one to introduce negative Gaussian curvature and this one to introduce positive Gaussian curvature. And you can balance the positive and negative Gaussian curvature and still close the structure. And people have observed, we proposed this some time ago, and people have observed that in grain boundaries or these line defect, extended line of defects, octagonal-like defects may be present. So this is taking the concepts of differential geometry and geometry to understand other structures. That of course you can calculate these and you can use to close these structures and get these fullerenes. It turns out the problem is that doing with first principles, these small size may collapse. You need to perform a bigger size structure. Bigger size implies having like 600 atoms or 800 atoms, and then you can calculate that with first principles. Now I will go very quickly. At what time do I have to finish? 3:45 or 4:45? Okay, so I will go very quickly, perhaps a characterization of two-dimensional materials. It turns out that one of the most important characterization techniques is Raman spectroscopy. And it turns out that you can calculate Raman spectroscopy in most of the DFT codes that are available. I will not talk about aberration-corrected TM or optical microscopy. I will not talk about photoluminescence, so I skip this. This has to do with a very interesting problem that has to do with the passivation of edges, but I will skip that and get into Raman spectroscopy. So here is C.B. Raman. He got the Nobel Prize in 1930 because what he found is that when he excited with monochromatic light a system, for example, a molecule, it can be a molecule or a crystal, you can take your system, you excite with light, and then you see how the light is absorbed and scattered by the system. And you may have the case that it happens, and happens all the time, that you excite with this laser, you get this exactly the same. This is called Rayleigh scattering. So nothing happened. So you get the same that you introduce. However, 1% of all these, if this is 99%, 1% goes to what we call Stokes and anti-Stokes. So you excite your system. These are your molecule. These are vibrational states. You take your molecule or your system to a vibrational energy virtual state, and when the structure absorbs and scatters light, you get that does not go to zero, this state, but goes to another vibrational state. This is called Stokes, and here you have Raman effect. Or anti-Stokes that you start from an already excited vibrational level, and then you end up in scattering with the ground state of vibrations. So Raman found these, and he got the Nobel Prize. And it turns out that with DFT you can calculate and make sense of experiments of the Raman spectra. This is the graphene Raman spectrum. This is the nitrogen-doped graphene spectrum. If you look, this is D, the one that is doped has a D band, this is called D band, has a higher peak. G, this is called G band, you have a G band, and also you have a D prime band. In this one that is doped, dope means that it's substitutionally doped. Some nitrogen atoms are substituting carbon atoms, and then you have these 2D. Well, you calculate the phonon dispersion, and the phonon dispersion gives you all the information. This was calculated with LDA. It's very good to use LDA. Gives you all the information on what happens in your system, even when your system is doped. And you have to check, you have to see just what happens at gamma, because you are exciting your system with photons. Photons do not have a linear momentum. So what happens at your excitation, you will not have a value in momentum because photons do not have momentum. So you just focus on the point which is gamma. This is called zero energy. In the Brillouin zone is the center of the Brillouin zone. And what you see is that these are called acoustic modes. There are only three acoustic modes in any system. And the ones you see here, these ones are the G band, around 1600. Here are around 900. These are not Raman active. And there are some symmetry and rules regarding Raman activity, but all the information is here. So at gamma, you see the G band. But what about the other bands, like the 2D, the D, the D prime? Believe it or not, are here. And it turns out that these bands have to do with resonance processes. For a resonant process to take place, then you have you need to use a particular excitation. So here, the D band is given by, in fact, is this one, these phonons, gamma K. The 2D band is twice the D band, but the D band is caused by defects. So that's an indicator that you have a defect. But it is shown in the phonon dispersion, even if you don't have a defect. You can visit. What happens is that you excite your electron to a particular point in your Brillouin zone, and then there can be a defect. If you have a defect, the defect will scatter your electron to a more or less the same energy. And I have a slide. And then there is a phonon, which is this phonon, that scatters your electron to another point in the Brillouin zone in which your electron can go down and produce the excitation or produce light. So this is double resonance. This is resonance by defects, and double resonance is that you excite with a particular excitation, and then your electron is scattered by a phonon, and this is scattered back by the same phonon. This is not caused by defects. This is one case that we solved in which we found that this 2Z phonon, 2ZA phonon, was responsible of this peak, and the information was here. This is the 2ZA phonon. And we calculated this was calculated with quantum espresso. Okay, so this is the diagram. You excite, in this case, 2.4 EVs for 88 nanometers laser. You get to this point, and then there is a phonon, ZAM phonon, that scatter your electron to this point, and then scatters back, and then you can recombine here. Is what you have here. This is T1 is here. So it's this point. This is gamma M phonon, ZAM phonon, which is here. ZAM, this is the wave vector. And so you touch this part. This is the isosurface of the isosurface. You cannot go to any place, just places where you have a value of energy or similar value, and then you can scatter back your electron. So this is called double resonance effect. So I think I will show you another case in which we found, by calculating the phonon dispersions, that there is a peak, this small peak, that appears, this small signal, in few layer systems out of tungsten diselenide are related to this band. If you have a monolayer, this is not going to be Raman active. But when you add more layers, this peak appears. So I calculated several layers and found that even with 3 layers, this peak appears. So all the time this peak appears, but it is not there with the monolayer. So we explained this peak, and now people agree that this is a first order peak for few layers. So you want to distinguish these systems with Raman spectroscopy, because Raman spectroscopy is not does not damage your sample. You can see if you have a monolayer or a bilayer, or what you have. I will not get into the details if I have just 2 minutes, but this is related to optical properties. It turns out that there are linear and nonlinear optical properties. In linear optics, you excite with a particular excitation, and you can induce dipole moment per unit volume, or a polarization in your system. And if you are in linear optics, you can express these polarization in terms of your electric field in this way. This is called chi1, and this is what happens in linear optics. But it turns out that in nonlinear optics, you can express your polarization in terms of this power series. And this happens when you don't have inversion symmetry. TMDs, semiconducting TMDs, do not have inversion symmetry. So you can have nonlinear optical properties. And this is very interesting because these chi2 and chi3 are called second and third order nonlinear susceptibilities. The second order nonlinear susceptibility is very closely related to what is called second harmonic generation. And it turns out that if you get the optical image of molybdenum sulphide, you see nothing, right? And when you calculate or you obtain experimentally the second harmonic generation image of molybdenum sulphide, is what you see. And these are these black things, or red, is another layer that is growing on top. So this is second harmonic generation image. And what we have done, and my student Corey, he has been working in calculating this second harmonic generation. I will skip that. In alloys of TMDs, in which we introduce sulfur on top and selenium on the bottom. These are called Janus. For different transition metals, these called, we call this SSEB, and is the way they named. And this is another way of studying these alloys. These, in this case, are alloys. We call them alloys, are ordered. Here we have a one transition metal, a different transition metal, and we can calculate the Chi2, which is related to the second harmonic. And we can see where we can have a good signal, what is the excitation, or this is half the excitation, because in the second harmonic, what you have is you introduce a laser. This is your nonlinear optic system. You have a laser of 800 nanometers, the wavelength of your laser, and this is a nonlinear system. Your laser, your wavelength will change to 400 nanometers. Your frequency will be double. So people that work with lasers in optics, to change the color of a laser, they use a nonlinear optic system. But here, it turns out that the intensity of the second order susceptibility is huge, orders of magnitude, 3 orders of magnitude bigger than the three-dimensional systems. So we are calculating this with and without excitonic effects. Here is DFT, and with BSC, that means introducing excitonic effects, solving the Bethe-Salpeter equation, we get huge differences. So the only way to study these systems, excitons in these systems, is using BSC, which goes beyond DFT. And with this, I close. Thank you very much. I would like to thank Michael Looking, my postdoc, Corey Beach, Ross Siegel, Zach Ward, and Yuhon Liu. Thank you very much.